I modeled the same truss 3 times, same geometry, same loads, but one of those models can push a real wall or column outward until it cracks. And the only thing I changed between these models is how the supports are defined: pinned, roller, or spring. So which one is right? I'll show you. When you apply vertical loads to a truss, the whole thing behaves like one big beam. And like any beam, it wants to bend. That bending pushes the top chords into compression and pulls the bottom chord into tension. And because the bottom chord is in tension, physically stretches and wants to get longer. Now, if you model both supports as pinned, like in this first model, you're locking both ends in place. They cannot move horizontally because it's a pinned support. It restricts horizontal movement, so you're trapping the truss. So essentially, the bottom chord wants to stretch, the supports won't let it, and that fight shows up as a horizontal reaction force at each end. As you can see, there's a 7.78 kilonewtons reaction pushing outward. So the truss pushes on the support and the support pushes back, equal and opposite. That's Newton's third law, action and reaction. You learned that in high school. Now the question I know you're going to ask is this a problem? Well, not necessarily. If whatever's under the truss is stiff enough to take that horizontal force, let's say a concrete wall or a chunky column that won't move at all, the pinned model might be a fair assumption. But we had a live call inside Bang Lab recently, and one of our members asked the question about trusses landing on lightweight framed walls. Now, these walls are not designed to take a big horizontal push at the top because they're flexible. So what's the issue? When you model both ends as pinned, you're telling the software the wall can hold this. And the software is going to believe you, right? It will never check that assumption. It just gives you results based on you asked for. However, in the real building, that 7.78 kilonewtons has to go somewhere. If the wall and the connections cannot resist it, the top of the wall gets pushed outward. And that's how you start cracking the structure. It's not ideal. Generally bad for the client, also bad for your stress levels when they start calling you. So one common way to deal with this is to release the horizontal restraint at one end of the model. We call that a roller support, like in this second model. As you can see, it still resists vertical load like in the first model, but it lets that end of the truss slide horizontally as the truss deflects. Now, before I show you the results, remember this. That 7.78 kilonewtons doesn't magically disappear. Forces never disappear. It has to go somewhere. So as you look at this second model, the question is, where did that force go? All right, so this is the roller support. The horizontal reaction is gone. The wall is off the hook because the truss can move freely. However, watch the bottom chord. In the pin model, the bottom chord was taking 0.79 kilonewton tension close to the supports and a bit of compression along the middle, while in the roller model, that jumps to 8.33 kilonewtons tension axial force. The bottom chord is now doing the job the wall was doing before. It's acting as a tie, holding the two ends of the truss together. This is exactly the same principle as a pitched roof with ceiling joists. I've got a whole video on that in the channel. You can see that the truss did spread 0.74 millimeters of horizontal movement at the roller. 0.74 millimeters, that's less than 1 millimeter. So keep that number in mind because it becomes important in a minute. So the force didn't disappear, it relocated out of the wall into the truss, and that means this truss carries more internal force and deflects more, so it might need more material to cope. So it might be a little bit more expensive than this first model. So you can see that one tiny button that I clicked on the software changed the design of the truss members. Now, if I can read your mind, I know the question you're asking yourself. How the heck do I actually make sure there is a roller support in real life? Because on site, both ends of this truss look exactly the same. They're both strapped or nailed to the top plate. Nobody went on top of the wall and installed a wheel on one side. And that's the thing. When engineers say assume a roller, it's a modeling assumption. There's no literal wheel sitting on your wall. Unless you deliberately detail it that way, you could use slotted holes, for example, but that's not the case. So here is what's actually happening. The connections and the wall framing itself have a small amount of natural flexibility. And remember that number from before? The truss only wanted to spread 0.74 millimeters. And in the real building, that's going to be shared between both supports. So 0.74 divided by 2, that's 0.37 millimeters at each end. So each connection only needs to give a third of a millimeter. A nailed connection into a timber top plate on a flexible framed wall can give you that much movement without even trying. It's a tiny movement. So the real behavior might be closer to a roller than to a perfectly rigid pin. And real structures are usually somewhere in between. They're not perfectly rigid pinned and they're not perfectly free like a roller. They're somewhere in between. And there's a support type for that, which we call spring. A spring support is telling the software that the wall has some stiffness. It will push back the truss, but it's not infinitely rigid. So if we have a look at this third truss model, I've got a spring at both ends, and watch what happens if I change the spring stiffness. If I crank it right up to say 100,000, 100 million kilonewton per meter, analyze, and I'll check the results. Let's say, for example, reactions at the support, 7.78 kilonewtons. What that reminds you, it's exactly the same as the pin supports, 7.78. Let's have a look at the deflection. We've got 1.16 millimeters. Let's go back to the first model, 1.16 millimeters. Let's have a look at the axial force, 0.79 here, 0.79. On the other hand, if I drop the stiffness down, let's say drop that to 100 and analyze the model again. If we check the results, reactions are very low, 0.04. Let's actually drop that down a little bit more. Let's make this, instead of 100, let's make that 10 kilonewton per meter. Now let's check the results. Reactions, there's no horizontal reactions. If we look at deflection, that's 2.16. What does that remind you? Well, it reminds you of the roller support. That's 2.16. There's no horizontal reactions. There is a spread of 0.37 millimeters at each end, which is basically the second model. But remember that we have a 0.37 millimeters at each end. That's exactly what we had here. So really a pin and a roller were never different things for this case. They're just springs turned all the way up or all the way down. Every support is a spring. Everything is a spring. Springs are beautiful. The only question is how stiff is that spring? And you can put a number on that with Hooke's law. F equals K times X. Force equals spring stiffness times displacement. We all learned this in school, somewhere around high school. I can't remember exactly. I'm too old right now. But it just means if I push the top of a column and it moves, the ratio between the push and the movement is the stiffness. So push it, it deflects a certain amount, let go, it comes back like a spring. As I said, everything is a spring. So here's my logic. Say the wall is 2.7 meters high and I'm comfortable with it swaying at the top, height divided by 600, right? That works out to be 4.5 millimeters. If the wall takes the full 7.78 kilonewtons while moving 4.5 millimeters, then its stiffness works out to be 7.78 divided by 0.0045 meters, 1728 kilonewton per meter, which was the initial spring stiffness that I had in this model, 1728. Now, is that the real wall stiffness? I have no idea. Probably not. But timber framed walls are composite assemblies. You've got studs, you've got plates, you've got cladding, nails, the tie down rods. So calculating the real stiffness properly is its own rabbit hole that we're not going to get into right now. So I'm not proving the exact stiffness of this wall. This is a rough, deliberate assumption to test how sensitive the truss is to the support condition. That's all I'm doing. Also, this stiffness is a bit on the high side because that 7.78 kilonewtons came from the rigid model. And a flexible wall will never actually see the full 7.78 kilonewtons. Anyway, so that's why for a truss sitting on a lightweight framing wall, I'll typically design the truss with a roller support, like in the second model. It's the conservative assumption for the truss. The bottom chord gets designed for the full tie force. I get the worst case deflection and I don't impact the supports. The spring model is how I understand what's really going on, but the roller is how I actually design the truss for. Now, in case it's a column supporting the truss, it's much easier for you just to model the column in the software and you're going to get accurate results. But if it's a lightweight framing wall, as I said, it's a bit more complicated to capture the whole assemble in the software. Now, there's one more thing that I want to talk about because there's one truss where this whole support question gets much worse. So what if the client wants a raked ceiling or what we call a cathedral ceiling? Now you're designing scissor trusses like these ones. And what's the problem with them? Well, what if I ask or Bang Lab knowledge base exactly that question? What is the problem with cathedral ceiling? Bang Lab knowledge base? I'm going to scroll down and you can pause the video if you want to. But basically the answer comes down to this. The bottom chords slope upward, which means they can't tie the walls together like in the standard trusses with the straight bottom chord. So think about the load path in a normal truss. The bottom chord in tension pull both walls towards each other. Every bit of that force is doing the tie work. However, when the chord slopes, if we break down into components, you know that part of that force is going up the slope, not across the building. So you've got the same force, but less tying action. So the truss tend to spread more. And you can see in the numbers, I'm going to show you another model. Now, this first one, let's just have a look at the results of this one for comparison. If we look at the deflection, pin supports go from 1.16 to 2.16. So that's about 2 times. Now, if we open the scissor trusses model and check the deflections, so from 0.54 to 8.01, that's almost 16 times more deflection. So 16 divided by double by 2 of the standard trusses, that's an 8 times more sensitive if compared to a normal truss arrangement for this specific example. So what does that mean in practice? Well, it means more spread, more deflection. So to get it to work, you have to really beef this thing up. It becomes a big daddy truss. And sometimes you can't even get it to work economically. So the key lesson is very simple. Pin, roller, and spring supports are not just buttons in the software. They are load path assumptions. And your assumptions need to match the real structure. Because if the real structure cannot provide the restraint that your model assumed, then your forces, your deflection, and your detailing are describing a building that does not exist. And that's where software gets dangerous because it will never warn you. It just answers the question you ask. All right, cool. If you want to learn structural analysis like this, apply to real residential projects in Australia and New Zealand, we've got a few spots left at the lowest price. Link in the description below, and I'll see you in the next video.